So good morning, ladies and gentlemen. Good morning. We continue with our course of quantum transport, lecture number 3. And there will be a slight change of topic. We're still talking about scattering, about a scattering approach to electron transport. We have studied it for the case of several channels in quite some detail. We look at interference. And today we would like to understand more about the systems with a larger number of channels. As we remember, number of channels roughly corresponds to conductance in units of conductance quantum. So we are talking about more conducting nanostructures. And what I would like to understand first is the correspondence between quantum mechanics, which is given by scattering approach, and something which we know and we take it for granted. I would like to understand correspondence with Ohm's law. Strange, my pen doesn't work today. Okay, correspondence with Ohm's law. All right, there will be many subtopics today. First of all, I will talk immediately how to get start from double junction, which we know, which we have described in the last lecture, and understand how Ohm's law is reproduced in these circumstances. It turns out that it is reproduced by averaging over phase shifts or self-averaging. If you have many channels, many phase shifts, and there's self-averaging going on, good. That would be one topic, perhaps most important. Right. Next topic, which I kind of how to say, feel myself obliged to talk something about. It's by this time a rather old-fashioned description of the transport. Namely, how do we describe electron transport in bulk solids? We don't make nanostructure, we just take a crystal, whichever, give contacts and measure its resistance. All right, that would be some road to follow. And we end up with finite-element approach, or in simple terms, with circuit theory, Kirchhoff rules circuit theory. Kirchhoff rules are, in fact, based on conservation law, conservation of charge, and we will spend some time trying to apply conservation laws of charge, energy to, again, to the double junction system, to understand how does it work in quantum transport, how does it help to understand the systems. Then I will depart to very advanced direction. First, we learned that in quantum mechanics, one can make more conservation laws than in classical mechanics. That sounds strange. There must be correspondence principle, but this is a fact. We will look at these examples of such extra currents, matrix currents, which can be conserved. And I will sketch for you a quantum circuit theory. Quantum circuit theory, which is in fact template for many concrete circuit theories addressing different aspects of quantum transport. I will talk in the end of the lecture about this template. Good. No questions so far. I would remind that I appreciate questions to the chat and appreciate it coming all the time. That gives me a very warm feeling. Basically, I have, it's yet another outline, but I just want to stress that in this lecture, we are making bridges, in fact, between which shores, between which two sides. One side is quantum transport, where electrons are waves, and transport is described by scattering matrix. On another side, we have classical electron transport. We are talking about electric currents, Ohm's law. We make circuits consisting of elements. Right. And again, we will make two bridges rather than one. There will be a simple bridge, and then we will derive Ohm's law, classical transport circuit theory from quantum mechanics. There is also room for a golden bridge when we learn how to utilize Ohm's law, classical transport circuit theory, described in the systems where quantum mechanics play a role. So all this with quantum mechanics. Fine. Let's get to double junction. The advantage of the system is that we know it in quite some detail. Remember, in the last lecture, we managed to compute full conductance through this double junction system by multiplying amplitudes and summing up amplitudes corresponding to different trajectories. There has been interference. We know the answer. Let me present this as a paradox. Suppose I don't want to go into formulas. I want to restrict myself to simple estimations. Good. So I take two junctions in series, and I assume that the transmission amplitude is much smaller than one. So in fact, those are two tunnel junctions. Fine. What would be an amplitude for a wave which traverses the junctions? It has to be product of amplitudes, right? How can I estimate these amplitudes? Well, from conductances of both junctions. Apart from conductance quantum, squares of amplitudes define the conductance. Right, the same I should do with conductance of overall system. What would I get? That is strange. I get that conductance scales as a product of individual conductances. Okay, I put here GQ to keep dimension. All right. Do you agree with this estimation? Apparently, something must be wrong or misunderstood here, because we know how we combine elements in kind of usual electron transport. Well, each junction of this kind corresponds to a resistor. And what we do, we just supposed to combine two resistors in series. So there is a Ohm's law. The resistance, total resistance is the sum of the resistances. I see the question, just a second. I will rewrite it in terms of conductances. That's what I get. And what is the difference? Okay, as a product is eventually here and here, but the denominator is completely different. If I increase both conductances here by a factor of 2, the total conductance will increase by a factor of 2. If I increase here all conductances by a factor of 2, what would be change of the resistance? Think about it. I will look at the question. The question is the approximation here that we neglect multiple reflection terms? In fact, that is, we will see that indeed they're important, but what I would like to stress that they do not appear in a simple estimation like this. We will come to this interference terms in a moment. Meanwhile, what is the answer? I use Ohm's law, I change all conductances G1 and G2 by a factor of 2. What would be change of the total conductance? A. Look, I really require your answer. If you don't answer such questions, then you kind of yes, right. Okay, of course. You just put factor of 2 or here, and you get factor of 2 on the left hand side. Yep, sure. While here it's a factor of 4, so it is a correspondence. Fine. How to deal with this? At the level of simple estimations, we are really in trouble. So what we do, we recall how do we compute the actual transmission through the system, right? We sum up amplitudes rather than probabilities, and we end up with this expression, which also depends on the phase fixture, something which is not present in either A or B, something which unites these two. So the spacing between these two contacts is described by extra phase factor chi. Good. Let me see what will happen if we average over phases. So, in fact, we don't sum up amplitudes anymore. We sum up probabilities. There are certain probabilities to get through the structure a certain number of bounces, and I sum up all them. This is equivalent to suppression of interference effects. And that's why averaging over phase delivers me that. Right, okay, and what I get, let me neglect terms which are small because probabilities are small. I got almost Ohm's law. I got the sum of conductances in the denominator. Great. Let me understand the paradox on qualitative level. So it's transmission plotted versus phase factor or energy. We know that phase factors depend on energy. One can plot it, transmission over energy. Let us see, what can I see in this curve? First of all, our naive estimation was correct. And actually it was correct for most intervals of the phase factor, except special value where transmission peaks to values almost 1, transmission resonances. Okay, so in transmission at peak is 1, so in average, if one average this and this, one gets something which is proportional to the transmission. This green line, which I made red, gives you average transmission. Okay, sounds funny, but in fact, Ohm's law is restored owing to transmission resonances, rather complex interference of waves. Fine, that we did for one channel, and we kind of average over this phase factor rather artificially, right? We could kind of make many identical structures with different phase factors. We can kind of sweep this phase factor, modulate it with a gate. But anyway, it would be rather artificial procedure. So let us try to do it for minor channels. First, what I would like to try is the following. I take many independent channels in parallel, which have different phase shifts and different periods with respect to energy, right? Different times of flight. Right, and in fact, I've plotted all that. I've taken 6 channels, and each individual colored curve gives this series of transmission resonances. And I just sum up and compute average resistance, which is given by this thick black line. Well, you see that fluctuations of resistance have become smaller, and it kind of corresponds more to average resistance. Well, if I add more channels, let me add more channels, I would get a curve which goes somehow like this. Right. So rather plain fact, if I take many parallel channels, the contribution of different phase shifts would be averaged. But we are not quite done. Look, if I just do it formally, mathematically, that's what I get. So for each channel, Ohm's law is restored. And I sum up over these channels, but it's not quite Ohm's law for the whole system. Here it is. I need to get conductance, I have to sum up over all channels. So how to deal with this? It turns out that kind of channels are not that individualistic. They don't cope with Ohm's law one by one. Rather, they do it together. How? For one channel, the space between electrons can be represented by a single phase factor. For many channels, from this single phase factor, we got a sequence of phase factors, and that can be seen as a unitary matrix. Unitary matrix with eigenvalues of unitary matrix. I don't remember if I talked about these are phase factors. All eigenvalues of unitary matrix are complex numbers of unitary modulus. Fine. And this unitary matrix basically mixes up all channels randomly. And if you assume so, you restore actual Ohm's law. So to get Ohm's law of two quantum scatterers with big number of channels, one has to make how shall I say? Let me remember this silly riddle: A and B, right? A and B, and appears to be rather complex object, unitary mixer, scattering matrix. And if you do so, we reproduce Ohm's law. We reproduce what we mean. And yeah, let me recall that it is actually due to transmission resonances which occur in the structure. So Ohm's law, which looks triviality for us, it is rather peculiar interference of the waves going through the structure. Fine, we have solved the paradox. We have restored Ohm's law. Where to go further? Let me add some, philosophy at this point. Not that I like philosophy, but sometimes it's needed to get kind of overall picture. So these unitary matrices, which are important in the case of big number of channels, they can be seen as a set of phase shifts. Right. The sizes of realistic nanostructures are at least several times bigger than the electron wavelengths. So the phase shifts are big. All possible imperfections in the structure are very easy to provide the wrong phase shifts, are very easy to affect and mix up these phase shifts. And it would be fair to say that the present day technology, what we have now in the lab, we cannot control phase shifts. We couldn't make a kind of a structure of even 10 conducting channels with all phase shifts controlled. If we will try to do formally identical samples, just taking the same prescription, mask, go to the lab and repeat, nanofabrication again, most likely they will have very different phase shifts. Right, I have a little drawing to understand why this happened. There is a disorder in nanostructure which one cannot control. there are fabrication errors in course of fabrication. So, for instance, this gate didn't quite work. But even if we work out all these Rome factors in the scale of nanostructure, there will be still disorder in the leads, which also affects propagation, which also adds phase factors to propagating waves. Right. And although we could tune everything for a single channel, perhaps for 2 and even for 3 channels, if we add more channels, we can have less and less control. Just because the number of phase shifts is too many, one has to control n by n matrix with n squared elements, so it goes up very quickly. Right. Okay, general principle. Let's apply it here. If you cannot control something, just let it go. Perhaps it will be fine. Or let me express it differently. All these unknown things, all these random things, well, actually ignorance can be frequently treated as randomness. We don't know the cause of something, and we presume that it has happened randomly. Sure, we don't know these phase shifts, but perhaps we do not have to know. Right, to kind of fix the situation, let me take analogy from another area from statistical physics, which actually shows that when it becomes really messy, it also becomes simple, right? Think of gas molecules in maroon. So zillions of them, every molecule has 3 coordinates and 3 values of momentum. They go around each other, they collide with walls. Many things are going on. But, well, I don't want to know about this. What I care about air in my room is just some overall quantities like pressure, oxygen content, temperature, right? So instead of zillions of parameters, I just care about 1 or 2 or 3. It becomes simple. Right, so it is just so simple. We have self-averaging over the channels. We cannot resolve the channels, and we characterize the transport through such a nanostructure just if a single number conductance. Right, self-averaging. If you take many channels, if you make structures with many channels, you are likely to produce same values of conductance if you do it correctly. While for few channels, fluctuations of conductance of the order of conductance itself. Good. So we can consider many channel structure. Don't have to write many channels and something in between. And this for for such nanostructures, Ohm's law is completely restored. I could, for instance, cut this nanostructure into measure resistance of this part, measure resistance of this part, and despite the fact that particles are waves, the resistance are destroyed. But there are circumstances when it is important that there's still some quantum mechanics and there. So the wave patterns in this nanostructure are very complex and not to comprehend, but electrons are still waves. As we learned in the last lecture, there are inelastic processes, decoherence, dephasing, which completely destroy quantum mechanics. So if one takes sufficiently big structure, these processes will destroy quantum mechanics. But there are, as I say, circumstances where for structures of this kind, quantum mechanics remains in there. It's just hardly visible, right? And what I will say in the end, what I will tell about quantum circuit theory, it applies to this particular situation. Let's see how I'm doing. Okay, I have still like 10 minutes to go till the break. Good. The concept which I tell you are not complex, but rather unusual. So if you have kind of simple questions, I will be delighted to answer those. If not, let me switch gears. I would talk about electron transport in solids. The people have recognized that this is a problem already about 100 years ago. Then they figure out that electrons in crystal periodic solids are eventually Bloch waves. Right? So I draw here a Bloch wave, an electron state with kind of equally spaced wave fronts. Everything is fine. And it's pretty good description of a solid if there are no impurities. Why it is bad? Because as it is shown in the picture, the impurities destroy this picture of plane waves. The scattering of the waves at the impurities, each impurity becomes a source of spherical wave, which also propagates. So even for 3 impurities and like 100 atoms, which I put here, the resulting wave pattern is a complete mess. Right? For some, actually for many quantities characterizing materials, one can neglect impurities because there are not that many. If one thinks, for instance, about heat capacitance, whatever, about hardness of the material, impurities do not matter much. But the conductance itself, electron transport itself, is completely determined by impurities. If you throw away impurities, and we try to estimate conductance, we would get something infinite, because without scattering, electrons would just go through the sample and yeah, without encountering any resistance. So resistance will be zero. To compute the resistance, one has to look at scattering at the impurities. Good, that was a problem which people have encountered almost 100 years ago at the at the very beginning of quantum mechanics. Well, people were smart already by that time, and they have figured out how to deal with this problem very quickly. In fact, they kind of said, well, down with the waves. Let us recall, let's get the original description of electron as a particle, electron as a ball, and it just goes, and if it if it finds an impurity, it scatters in this impurity, then it could scatter in another impurity, and so on. Right, that's a very kind of sketchy way. How do they proceed? So what I will do now, I will try to formalize this for a bit, add some formulas, and then we will see what we get. That's also kind of illustration of the methods which one can utilize in this aspect. Good. Let us see. What's the quantity to look at? So the crucial step is to understand that we don't go for complex wave patterns. Rather, we can think of distribution of electrons. There are many electrons. Distribution of electrons in the space of coordinate and momentum. We've been talking about this filling factor already. It was a function of energy. So it could be a function of momentum. If there's thermodynamic equilibrium, we could replace it by Fermi distribution. If there's transport, one cannot do so. Remember, even for quantum transport, filling factors were different at different sides of the nanostructure. So one has to consider deviations of this filling factor to see how does it evolve in space and time. One could proceed actually precisely quantum mechanically using Schrödinger equation. One could define this distribution, this filling factor, which depends on x, with the help of quantum mechanical formulas. So we kind of make a sort of density matrix. We sum up over all field states. That's what we get. But it appears rather impractical in view of the fact that we can use conservation law, a conservation law, number conservation of particles in a small volume of 6-dimensional space. 3 for coordinates, 3 for momentum. So number of particles in a small element of this 6-dimensional space is always constant, but the element itself moves in time. So from total derivative, we got to write partial derivatives. And that's what conservation of particles gives us. Let us see. So there is a time derivative. So this is an evolution equation. And a change of coordinates gives rise to derivatives with respect to coordinates. Change of momentum in time gives the derivatives with respect to momentum. Right, now we can recall that this is eventually velocity. It depends on momentum. And this is a force, which depends on coordinates. So we have a closed equation to solve, which is called, who knows how this equation is called? But you have seen it at least once in your courses. Which one? Let's see. This equation. No, not really. Okay. I'm sorry. I'm pretty bad continuity. Well, in fact, it's continuity equation, but in 6-dimensional space. Usually, one writes continuity equation in 3 dimensions. We'll come to this. This is called Liouville equation. I feel ashamed, but I'm pretty bad in French spelling. I don't care to write it down, but yeah, it sounds like Liouville. Does it ring the bell? Liouville equation also kind of applied in many areas, like in hydrodynamics and gas dynamics, in many sense, because we always kind of deal with particles. In many cases, we deal with particles which move. Okay, Liouville equation. Good. Fine equation, but well, it doesn't contain what we want. It doesn't contain impurities so far. We have to supplement it with scattering on the impurities. Unfortunately, we can do this with rather simple considerations, perhaps rather boring considerations, and we will see these considerations come in a couple of times in our course in the form of master equation. So this is a probability balance, something for bookkeepers. Sasha, I wouldn't call it a generalization, but anyway, let me talk first about this scattering, right? So what happens with the scattering? It randomly causes transitions from, let me see, from the state pi prime to pi. Transitions with change of momentum. Electron comes to the impurity, it deviates in case of scattering. So one can introduce probabilities per unit time to have a scattering event, right? And one can plug in it into this equation. There are two terms. That's why I recall bookkeeping. There are terms which describe probability loss. And in this case, look, we look at filling factor at probability at P, and it scatters to all other states. So I sum up over all other states. Probability to be in states P gets lower because of the scattering. That's a kind of expense. What is income? Other states which are occupied states by prime also can scatter and go precisely to pi. Right? So in this balance, in this bookkeeping balance, there are always two terms coming. We will also see when we talk about Coulomb blockade and transport over there. Good. So what equation do we reach? It is called Boltzmann, or in more general terms, master equation. Equation for probabilities under these circumstances. All right, I guess it's a good time to have a break. Let's have 7 minutes break. So we will come together at 9:40. Let me stop the recording. Thank you. We are at the stage of Boltzmann equation. It is rather complex. We would like to simplify it a bit. And that will work if one considers scales at which electrons have already collided with impurities many times. Okay, let me sketch electron trajectory. It goes, it scatters. That distance is a mean free path distance. It depends on impurity concentration. And let us concentrate on the space scales, which are bigger. Then at this space scales, the filling factor will become completely isotropic. Well, just because all scatterings have already happened, so the momentum has the information about momentum has been already lost. Still, energy is conserved during all these processes. We assume elastic scattering. So the filling factor becomes a function of energy. Right. And under these circumstances, we can write an equation for this function only. And that's gonna be, that is something which you also in principle know from other courses. This is drift diffusion equation. Drift diffusion equation. It is convenient for me to write it in a less common but more comprehensive form. It is as follows. The filling factor is like number of particles at a given energy per cube of coordinate space. And its change in this cube is a flow of the vector, is the convergence of the flow from this cube. Right? So there's a cube, there's current here. In this direction, there flow here in this direction, and the difference between these flows is a change of number of particles in this cube. All right. So what is the flow? The flow contains two parts. First part is the drift. We have force which acts on a particle, and there's some flow related to this. Another term is diffusion. In this case, the flow is proportional to gradient of the filling factor, of the density of particles at given energy. Two terms. Funny enough, but it's a rather fundamental topic of statistical physics, that both terms are related with the same, are proportional to the same diffusion coefficient. How to prove this? One can consider, for instance, stationary distribution, which is produce some potential. Right, in this case, it would be thermodynamical distribution. So the current from drift must be compensated by diffusion current. That's why they come with the same coefficient, diffusion coefficient. Okay, we start simplifying. Let's go on simplifying. Let's get it as simple as possible. Sir, I will integrate this equation over energy. Let us see what I get. If I integrate filling factor of the energy, I just got concentration of particles. Let me multiply it with electron charge. I got charge density. If I integrate flow over energies, I got electric current. So the first equation on the integration just became conservation of electric current. Now integrate this one. I have diffusion proportional to the gradient of charge density, and I have drift term in the current proportional to electric field, because electric field is a force which acts onto the particles. Right. Conductance. Important coefficient is conductance, and all this machinery was eventually to determine this conductance. If you have a uniform material, it's just a number. It depends on the impurities, it depends on their concentration, on many things. One can evaluate this with Boltzmann equation. Fine. Let us see. Oh, I've forgotten to say that in metals, charge density in the belt, not at the surface, charge density is 0. Good metals are electrically neutral, which means that I would replace rho by 0. Electric current must be divergenceless, and there is no this term. Okay, so I combine these two, and I get to still second order differential equation. Right, so if this conductance is a function of coordinates, it's a rather unpleasant equation to solve. Second order of second order differential equation in partial derivatives. So suppose one wants to estimate the resistance of such a metallic piece. So how would one set up the problem? Well, just model it with this equation and put it into computer it runs in several hours, you have the answer for your problem, right? Yeah, I'm saying not. Because just in order to design, invent computer, much simpler things than computer, one has to understand and model current propagation in such funny pieces. So there's seems to be what the Englishman call catch-22, closed circle. In order to invent, in order to solve this problem, a computer is needed, but to invent a computer, one actually needs to solve such problems. Right. Seemed to be no way about, and that was this closed circle, kind of vicious circle, has been broken by this guy, whose name is Gustav Kirchhoff. What he figured out, and that was really a revolution in thinking about electricity, what he has figured out that one can apply finite element approach to such systems. For instance, this one, with some accuracy, it can be replaced by 3 resistors. Okay, those 3 terminals, right? There can be voltages applied to each. Terminal. Right. And how to compute currents corresponding to this voltage. Let us recall it a little bit. One has to use Kirchhoff rules. The currents through each connector are given by corresponding conductances and differences of voltages at each conductor. So they are known for each element, but not for the whole circuit. What to do? One has to implement a current conservation. Yeah, this circuit is simple. We have only a single node. The sum of all currents into this node must be 0. Charge conservation. And from this, we have equations to determine the voltage in the node. And then we can compute currents through each conductor. It's important to recall circuit theory at this point. It's important to recall Kirchhoff rules at this point. Did I said everything in order to refresh your knowledge? Do I have to say something else to put it in a bit more comprehensive way? Please respond. When I was a student, I really hated circuit theory and stuff like this. I thought it's a little bit primitive. From the other hand, it was difficult for me to deal with discrete elements. And yeah, I was kind of rather irritated. It's only in advanced age I learned to appreciate this theory. And in fact, it appears to be, as I said, useful in quantum domain. Before going to quantum domain, let us shortly understand that we could do much, especially at the stage of circuit theory, with a simple conservation law conservation of electric current. Let me look again at this double junction system and let us see how we can figure out its behavior using different conservation laws. First of all, I assume that the structure is short enough, so all the scattering in the structure is elastic. Right, and I would like to apply conservation law to figure out what is going on in a node between the junctions. How can I characterize a node? I can characterize it with a filling factor in this node. Again, there are some states in between. I would like to assess filling factor of the states. How can I do this? Right. Let me compute the current through first junction. I will utilize Landauer formula. So there will be difference of filling factors at each energy. Let me take the current through the second junction. Again, I see difference of filling factors. So it's very similar to what I do when I would compute the voltage. Instead of differences of voltages, I would have differences of, I have here the differences of filling factors at each energy. Okay, now I utilize the conservation law. The sum of these two currents must be zero. I immediately get filling factor. Look, it's a superposition, linear superposition of filling factors on the left and on the right. Coefficients are proportional to corresponding conductances. Good. That's how I come to this plot. So remember how I plot the filling factor. Filling factor is on horizontal axis, energy on vertical. So I applied voltage difference. So the steps of filling factors on the left and on the right are at different energies. What's important for me, and I will recall it yet in the course, that in between I have a distribution with two distinct steps coming from the left and coming from the right. Good, I can compute now full current, and yeah, if conductances don't depend on energy, I reproduce Ohm's law. Fine, let us apply a different conservation law. In this case, it makes sense if the structure is long and electrons do collide when they go from one junction to another junction. They collide with each other, they exchange energy, and just assume Fermi distribution. They assume Fermi distribution, which is characterized by temperature and chemical potential. But it's not an equilibrium Fermi distribution, so we don't know yet this temperature and chemical potential. How could we determine these two quantities? All right, I'm gonna use two conservation laws, conservation of current, and now I integrate. Only full current is conserved, right? Scattering is inelastic. There's no conservation of flow at each energy. Full current is conserved, and I have to care about energy conservation. So I define energy flow through each junction. Good. And I have two conservation laws. So this gives me two equations to solve for two variables, for chemical potential and for temperature. Good. Chemical potential is a superposition of two chemical potentials. while temperature is usually of the order of voltage applied. That's why I kind of plotted here as a very smooth distribution with the width of the order of voltage applied. Good. Summarization, we still could make good use of conservation laws. Current does not change. Eventually, current noise changes. But yeah, let us not discuss this topic at the moment. Let us see what else. Right. Third situation, very simple one. Suppose the junction is so big that it can give energy to the environment. Well, suppose it's part of a computer, and I just put a fan, a cooler to this. Well, okay, and this works efficiently. So as I see, there's a rather sharp step also inside. So the temperature is low. So heat conservation doesn't work anymore because heat goes away from the space between the junctions. Again, we reproduce Ohm's law once again. Good. This was about rather trivial applications of conservation laws. And I talk about this also to demonstrate that all the different cases actually follow the same template. Which has a different physical meaning. In all cases, we have been talking about currents, flows, charge or energy, either the same energy or at the total flows summed up over energies. In any case, we a part of a template that we use conservation of these currents. Right. So all applications of classical conservation laws follow the same template. Now I'm want to talk about quantum circuits, quantum circuit theory, about quantum mechanical conservation laws. And let me first understand the situation which I would like to address. It is so that in the situation which we now, if we neglect an elastic scattering, the quantum mechanical coherence remains. And Ohm's law is restored due to disorder, due to the averaging in the structure, but eventually it cannot deny the fact that electrons are waves. So it conserves coherence. Simultaneously, it conceals coherence, quantum mechanical coherence, because all interference patterns are eventually gone because of averaging, right? There are some ways to reveal this coherence. One could look at the noise. As I mentioned, noise is very different, depends on quantum mechanical things inside the nanostructure. There are traces of interference, quantum corrections to conductance, which we'll describe. In lecture number 9, when we talk, there will be special lecture about these corrections. There are also magic mirrors, which are in quantum transport, are presented by superconductors. We will talk about this in lecture number 6. All this means to reveal the coherence experiment. Right. But of course, this coherence can be destroyed by inelastic scattering, or for instance, by noise tension disorder, by time-dependent fluctuations. And we will talk about this in the last lecture. Good. But now let me get to my favorite point. Let me, shall I discuss magic mirror first? Okay, let me say a couple of words about magic mirror and how it can be visualized in quantum transport and real life. Let us first consider common reflection. You remember quantum common reflections. There's incident waves, is reflected wave. And in this case, it basically follows different direction, different wave vector, right? Except it is really perpendicular to the surface. So that's common reflection. One can arrange the surface in such a way that it's a retroreflection. In this case, the reflected wave follows, goes in precisely opposite direction. Okay, precisely, it's a kind of technical with some accuracy, it goes to opposite direction, retroreflection. You might think that this is magic, but yeah, with a large probability you have seen today, unless you don't go out, at least you really don't go out. If you do go out, you have seen today a retroreflected mirror, where that was the question. Where do you see such mirrors? Give an example. Yes. Very good. Very good. Very good. Very good. Right. Actually, I meant the backside of your bike, but it's also kind of the same surface you use in road signs. The same you can find at the back of a car. It's just a surface which is modulated in this way, and with high precision, there's retroreflection from the surface. Fine. So there's no magic, just technicality. What would be really magical is a phase conjugated mirror. Look, in retroreflections, the phases of these two waves are not the same, they're opposite. So there's a phase shift which is accumulated if I go from here to here. What would be really cool is to have reflected wave in opposite direction. It is precisely same phase, so that the phase shift is compensated if I go there and back. All right, that cannot be the wave of the same sort, obviously. So I draw it with a different color. Red wave is reflected to blue wave. So it's called phase conjugated mirror, and it's really a piece of magic. One can do it for light eventually using nonlinear optics effect, very much pumped laser cavity. I don't want to talk about this at the moment. Electrons reflecting from superconductors provide us an example of magic mirror. I will talk about this in lecture number 6. But I just want to use it an example for conserving currents. Conservation of current on quantum mechanics. So you have studied quantum mechanics, you have seen different books, how to figure out whether the book you have taken was good or less good. There is a simple criterion. Good books contain the derivation which I put here. You might have said, well, my book was this book with a cat, with a Griffith's cat. I don't like misuse of cats in quantum mechanics. And it was a good book. This derivation was not there. It was. You just didn't pay attention to it. Few students pay attention to it. It's all right because it seems rather boring derivation, but it has to be there because it's very important. Look, we've been talking about probability in quantum mechanics, and one of the foolproof checks is for quantum mechanics generally as of a science, is to show that probability is a conserving quantity, which means that the current of probability does not diverge in stationary state. Okay, so that's why this derivation is there in the books. So how does it go? They say there is a wave function which obeys Schrödinger equation of this kind. And let's try the following expression to represent probability current. It's made of two times wave function and gradient operator. Gradient because current is velocity, velocity is momentum, momentum is a gradient. Fine. There's more or less direct computation of divergence of this current using the properties of Schrödinger equation, which finally shows that the current is zero. So it's all okay. Quantum mechanics is consistent theory. Well, usually people stop there. But there's a simple extension of the same reasoning. I will do it immediately. I will apply it for two wave functions which obey the same Schrödinger equation. Let me find the current in this way. So for any pair of solutions, I can define such a current, and I use the same machinery to check if divergence is zero. If divergence is zero, unless divergence is zero if the energies are precisely the same. Okay, if energies differ a bit, I can think of approximate conservation of the current. But anyway, there is a conservation law for any pair of wave functions. It's not probability, it's something else. But this conservation law persists. Let me give a couple of examples. Rather logical example is spin current. Let me recall that wave functions of electrons have two components, spin up and spin down. So it's like two wave functions I just had in the previous transparency. Let me make a matrix current in this way. So there is index of one wave function, index of another wave function, and I will write this expression. It has, this is a 2 by 2 matrix, right? And this is a matrix which encompasses usual current of probability, as well as spin current. Good, so I can now sum up overall wave functions. I would get the total current of all electrons, and I can write continuity equation. So there is a density matrix with spin index. It shows density of electrons and also density of spin. This is divergence of this current. So in the absence of spin interactions, like spin orbit interactions, which are usually very weak, there is a conservation of spin currents. We will talk about this in a week. We will talk in more detail about spin currents. That's one example of conserving matrix currents. Another example which you can give, it is for magic mirror. Remember, in magic mirror, we also have two components, two different waves. A reflected wave is not the same as incident wave. So to describe reflected radiation, I need to use the two-component wave function. Again, I can use it as an index and form a matrix, which gives a conserving current. Okay, in this way, I've understood there's plenty of conserving currents in quantum mechanics, eventually much more than a classical world. And for quantum coherent systems, one can find the way to apply the conservation laws for this current. Fine. So before I kind of sketch a template to use classical conservation laws. Now what I'm going to do is to sketch a template of quantum circuit theory. That's rather unusual, but well, it's a template. So and we will utilize it in a week on several occasions. We will see how does it work. But first, the template, which is rather symmetrical. Good. We have matrix currents. Correspondingly, we have matrix voltages. And these matrix voltages, like usual voltages, are fixed in the reservoirs, in the leads. So it's a matrix. There are some couple of special properties for this matrix. This matrix is traceless. And the square root of this matrix is 1. What does it mean? Actually, any matrix which has eigenvalues plus minus 1 satisfies this condition. Good, that's going to be matrix voltage. I called it with letter G because of some relation between Green's functions, electronic Green's functions, and this matrix voltage. But I don't talk about this. Rather, I will give examples. It's how we fill in the template. For instance, I would look for a circuit theory which just reproduces Landauer formulas. Landauer formulas, filling factors are important. My matrix voltage would look like this. If I would like to have something more, if I would like to take into account that there are different filling factor for different spins, I add spin directions, so each filling factor will become 2 by 2 matrix with a spin degree of freedom. If I would like to describe something like full counting statistics, well, I can achieve it with modifying this matrix, adding extra parameter, which is a parameter of, you remember, characteristic function of statistics of electron transfer. If I want to describe a structure which is in contact with superconductor, again, I can present it as a matrix which has the same properties. Trace is 0, squared is 1. There are different ways to fill into this template to get different quantum circuit series. What is common for all these quantum series? What are other elements of the template? We've been talking about nanostructure as in scattering approach, and we know that in this case, all transfer properties are determined by a set of transmission coefficients. Each channel gives rise to transmission coefficient. There's a set of a big number of transmission coefficients. It turns out that any matrix current between two leads is described by the same expression in all quantum circuit series. This expression is non-linear, a bit involved, but it is the same for all quantum circuit series. So in order to get the current, one should know the matrix voltages on the left and on the right. And yeah, it works like a current voltage relation for elements of usual circuits as Kirchhoff law. Good. So for any connector characterized by a set of transmission coefficients, we know the matrix current. Let us make a step and let us utilize the conservation of the current. In this case, we do an assumption. We do an assumption, and it's like an assumption we did when we consider double junction one. We say that a node in this structure becomes a reservoir, can be treated as leads, so one can ascribe matrix voltage to it. Like you can ascribe voltage to a node in common electric circuits. Good. Then the machinery which we can implement, and this assumption works if there are sufficiently many conductance channels, if the conductance is high, right? But I have already mentioned this. So if you apply this, one writes a series of Kirchhoff laws for this matrix current. For each node, the sum of matrix currents from all connectors, for instance, this is connected to the two, sum of two currents, is 0. And that gives us enough equations to determine the matrix voltages in the nodes. Then one computes current in the whole circuit and enjoys the result. So that was a template of quantum circuit theory. Let us see how I'm doing with respect to time. I'm doing pretty well. I could shift it to the next lecture, but I think I will start now. We will talk about it in more detail in the next lecture. Now I would like to just give the minimum example of useful circuit theory. Right. This is a circuit theory of transmission distribution. So suppose we know we have a connector with many T's inside. We don't care about individual T's. There are many of them. We know what is the distribution of these values. All right, so connector is characterized by a distribution of T. Then let's put another one in series, and there will be another distribution of T's. So we have two connectors in series. I would like to understand transmission distribution of the whole system. Right. Okay. And now I'm going to illustrate how circuit theory works, quantum circuit theory works in this case. We need to define matrix voltage. In this case, I must confess this matrix voltage is pretty auxiliary degree of freedom. I don't think it ever occurs in nature, but we just use it in order to formulate conservation laws. Still, conservation laws, which we are going to use, are specifically quantum mechanical. We should not we don't have to have something physical for this matrix voltage. Right, and we choose it in the simplest way. Simplest matrix is 2 by 2 matrix, and we would like to find a matrix which is traceless, and I just put zeros in diagonal to make sure that it is. And right non-diagonal matrix elements are these. So there is a matrix, and one can do multiplication, and to show that square root of this matrix is 1. Okay, with this one can compute the current according to the formulas, general formulas, and one sees that the current depends on transmissions. It eventually dependence of current on phi gives transmission distribution in some form. The playback formula is somehow involved. Okay, dependence of current on phi goes here. There's some algebra of complex numbers. But well, one gets the distribution. So there's a distribution link between transmission distribution and the shape of this function I of I. How to implement circuit theory? Okay, I will talk about more about the circuit theory in last lecture. Let me just flash what I want to make. Well, I have two elements. Each is characterized by function I of phase. I put these two in series, and I implement current conservation to determine the phase in this node and to find overall dependence of current on the phase. And this will give me the possibility to find the transmission distribution for resulting circuit. Good. I guess I'm done with all topics of today. Good of me. I did it precisely on time. So let me stop